Hi children, so thanks for watching. Welcome to TT Room Maths classes. So today we will see one of the important topic, that is real numbers for SSC as well as CBSE, almost the same. Both are on par according to the syllabus. So this is a first chapter as well as a most important chapter. You can expect around 10 marks. So let us see what we have. So in this chapter, you have to know what are number system and as well as Euclid division lemma, terminating or non-terminating, and fundamental theorem of arithmetic, and prove that the irrational numbers and logarithms. Now let us see what do you mean by number system. So actually numbers are number system basically two types. So real numbers and unreal numbers. So unreal numbers are usually in the form of a plus ib format or else root negative n format. So example, root minus 4, root minus 7, so root minus 10. So these are called unreal numbers. So you never seen, generally we won't see this type of numbers. So with under root we have number, we have seen, that is a plus 4 or plus 7 like that. But if you keep the negative sign, so they are called unreal numbers, also called imaginary numbers. So this part, this branch we won't discuss now. We'll focus on real numbers. So real numbers are denoted by capital R. So under real numbers we have rational numbers and irrational numbers. So mostly our focus is on this only. Now rational numbers are, as you know, denoted by q, which are in the form of p by q, though decimal numbers which are non-terminating recurring numbers. Example, 10 by 3. 10 by 3, if you divide, you will get 3.33333. That is called non-recurring, means never ending and terminating. So there, for short, you can say NTR. So non-terminating recurring decimals can be written as rational numbers, which are generally in fraction form or p by q form. So under this you have non-decimal numbers. So under non-decimal numbers you studied in lower classes natural numbers, whole numbers, integers, and under decimals. So further you can classify into under decimals terminated. Terminated means there is an end. Under terminated 0.75, 1.26, 25. So these are terminated. And here non-terminating recurring. Non-terminating recurring. Non-terminating means no end at all. Recurring means which are repeating. Example, just now I told you. So 3.33333, so on. There is no end. And 3 is repeating here. So example, 10.121212, so on. So these can be written as 10.12 bar. So these are called non-terminating recurring. So this branch is not so important for us, but we need to focus on irrational numbers. Irrational numbers are denoted by q dash or s. S equal to here squeezing numbers, not sneezing. Squeezing numbers. Okay, squeezing numbers. Now let us see what you have under irrational numbers now. Okay, so irrational numbers, okay, irrational number, they are not irritating numbers. So which are denoted by q dash or s. Okay, so you can write three different definitions for this, which are not in p by q form. Not, should not be in p by q form. That is the first definition. So, and also we can write as which are in root n form, where n belongs to natural numbers, means n should be natural number, and n equal to n should not be equal to perfect square. Okay, non-perfect natural number. So n cannot be 1, n cannot be 4 and 9, so on, because root 1 equal to 1, which again rational number. Root 4 equal to 2, so that is equal to 2, which again rational number, not irrational number. But what is irrational number here? Root 2, root 3, root 5, root 6, root 7, root 8, root 10. So these are the irrational numbers up to 10. So that is what the second definition. And the third definition is non-terminating and non-recurring. Means there is no end. Example, pi value, that is 3.142857, so on. There is no repeating number, no period. Okay. So 1 4 is a different number. No particular numbers are repeating here. So these are called non-terminating. Means no end, non-recurring, no repetition. So these are called non-terminating, non-recurring, which is also called irrational numbers. Three definitions I told you. So but the best, simple definition is the numbers which are not in p by q form. And we require now, this is important for you, because actually we mostly work on non-terminating and non-recurring, and we have exclusively one question. So you can expect in exam that given one fraction will be given. So check whether it is non-terminating or terminating. So then we will decide it. Okay. Now, so let's make a final view of the this one. So the number system. Actually, as I told you, so this is actually q. This is q dash irrational number. This is real numbers. This platform universal set. So is r. So q, under q will be having integers, and under integers you will have whole numbers and natural numbers. So all the every natural number is rational. Similarly, remaining all. So here irrational numbers you will be having root 2, root 7 and pi. So 22 by 7 comes under rational number, children, because denominator not equal to 0 and p comma q should be integers. This point also very important. So q can be written as, so any number can be in fraction form, p by q form. It can be it should be positive or negative. So but the fraction definition is different. Fraction should be only written using natural numbers only. So numerator denominator must be positive where while we are talking about fraction, but here rational number it can be negative also. So it should be in p by q form. Okay, and denominator must not be 0. P comma q must belongs to integers. So then only it is irrational rational number. Okay, example root 2 I have. Root 2 can be written as root 2 by 1. Oh, nicely it is in p by q form. But is it rational number? No, because denominator is okay, that is integer, but whereas root 2 is a irrational number, no. So it is not an integer. As per the three condition, p by q form, it is there. Q not equal to 0, that is also satisfied. P comma q, numerator denominator must be integers, but numerator is not an integer, so that is why it is not rational number. Okay, now let us come to this one. Let us make a relation between rational and other number systems. We can make a relation here. Natural numbers subset to whole numbers, whole numbers subset to integers, integer subset to q. Okay, so that's all. Okay, so that is a one relation you can make. And the second relation, q plus we can write as union, q plus q dash equal to real numbers. Okay, rational and irrational together forms here universal set. It is treated as universal set, means a very big set. So means remaining these two sets are number systems are derived from real numbers, no, or part of real number. So we can make this relation. Okay, now let us see few important points about number system. So which are important or which already asked in the previous exam. So you need to understand certain numbers here. Okay, so prime numbers you have to understand, and composite you have to know. Okay, and that's all. Mainly these two are important. Okay, so as you know, prime numbers which have only two factors, or else a number which is divisible by one end itself. Example 2, 3, 5, 7, so on. Okay, here you have to know one more important point. There are 1 to 15. So there are 15 prime numbers. If you strike out this 0, you will be having 15. And 50 to 100, you will be having 10 prime numbers. If you strike out the last 0, 50. 50 not possible, only 10. So totally from 1 to 100, 25 prime numbers. That is point number 1. And the next one here, so other than prime numbers, the number which has 3 factors, 3 or more factors, okay, 3 or more factors, that is called composite number. So here C is the third letter in English, so therefore like that also you can remember. So 4 is the smallest composite number because it goes in 3 tables. So that is 1 table, 2 table, 4 table. Similarly 6, similarly 8, similarly 9, similarly 10. Composite cannot be a prime number because prime number will be having only 2 factors, but composite have 3 factors. More than 2 factors, that is called composite, or is 3. C, composite means C3. So which has 3 or more factors, that is called composite number. Okay, right. And here one special number is there, 1. So this is already asked in the exam. So which of the following is neither prime nor composite? So, or which of the following is not a composite number? So options will be given. Out of the 4 options, 3 are composite numbers, but 1 is not a composite number. So it has no 2 factors, it has only 1 as a factor. So that is why it is not a prime. And it is also not a composite because it don't have 3 factors. So one is called neither prime nor composite. From 1 to 100, let us see some statistics here. So what do you call, 25 prime numbers are there, prime, and 1 is neither prime nor composite, no prime nor composite. And 25 minus 100, 100 minus 25 equal to 75, 75 minus 1 equal to 74, 74 composite numbers are there. Totally we have 100 numbers. Out of 100, 25 are prime, 75 are non-prime. Out of 75, one number is there, 1, which is not prime nor composite. So 75 minus 1 equal to 74. 74 composite numbers are there. Okay, so this part again important during the second chapter sets and the 13th chapter probability. Okay, so there these numbers, especially 1, 2, 3, these 3, and this part also very important. Please concentrate. Okay, now let us see, let us continue the next topic. Yeah. So I forgot one more point, that is a co-prime. Okay, now co-prime also called relative prime. Co-prime, because this part is useful while you are proving irrational numbers. Co-prime also called relative prime. So two numbers are said to be co-prime if they have common factor 1, or HCF of two numbers equal to 1, then they are called co-prime, or else GCD, greatest common divisor, which is also called HCF again. So HCF of any two numbers equal to 1, they are called co-prime. So here you see word prime, but the numbers need not to be prime also. Example, see here. So 9 is not a prime number, 10 is not a prime number, but both are co-prime because 9 goes in 1 table, 3 table, 9 table. 10 goes in 1 table, 2 table, 5 table, 10 table. Both have one common factor. So therefore both are co-prime. Okay. Also called relative. See, relation means one bond should be there. So likewise, two people are said to be relatives. They must have one bond. So here also two numbers have one bond, relative primes. Okay. Every two prime numbers always co-prime because so any two prime numbers you take, they don't have any common factor other than 1. So they are also called co-prime. Okay, right. So the first topic is completed here. Now let us see Euclid division lemma. Okay, so Euclid is actually called father of geometry. So Euclid division lemma. So for shortcut we can write EDL. So first of all you have to know what do you mean by lemma, which is a proven statement, proved statement, useful to calculate HCF or the number patterns. Okay, so this is also called it is very similar to old division algorithm. Okay, old division algorithm. What is division algorithm? If I divide, 7 by 2 if I divide. So 7 divided by 2, 2 3 is 6, remainder equal to 1. So 7 we can write as 7 equal to 2 times 3 plus 1. So 7 equal to dividend here, 2 equal to divisor, 3 equal to quotient plus the r. So this is nothing but Euclid division lemma. Almost very similar. But the thing is, we write here instead of this, instead of divisor, we will write any positive integer. Okay. So any positive integer. D instead of D, I have written A. A means any number. I mean any positive integer. So D means B. B is a divisor. Q is will be like that only, BQ plus R. So this is called Euclid division lemma. We know very well, remainder always less than the divisor, compulsory. Okay, when you divide, see, remainder is always divisor less than divisor only, no? So sometimes it is 1, sometimes it is 0, sometimes it is a different number, but however it is always less than the remainder. So that is the condition. And remainder can be 0. Okay, remainder can be 0 and remainder can be less than 0. Sorry, greater than 0. So this, if you read in a reverse manner, or greater than or equal to 0, what does it mean? Remainder, you can get 0 or you can get more than 0, that is a positive number. Okay, so and remainder should be less than divisor. So this is the condition. So this is called Euclid division lemma. So what is the use of Euclid division lemma? First of all, so to find out HCF of huge numbers, 4 digit, 5 digit, 3 digit, of course we have 2 digit numbers also there here. So but usually we take a very big number. So we'll find out HCF using Euclid division lemma. That is the main advantage. And also to study the number pattern. Okay, see, like prove that square of any positive integer is of the form 3p comma 3p plus 1, or show that every positive odd integer is in the form of 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. So like that. Such number patterns we can study using the Euclid division lemma. Okay, right. But here remember, don't forget, so all the terms which I have taken here, actually a comma b are any positive integer. So I am writing bq plus r. Okay, so this is Euclid division lemma. A comma b belongs to positive integers. Okay, positive integer. Of course, actually this Euclid division lemma, Euclid states that he stated that this is only applicable for positive integers, but it is also useful for negative integers also we can apply. Okay, so and whereas q comma r belongs to whole numbers here. Okay, so but here there exists unique pair. Only one pair only satisfies with any integer when you take. So that will satisfy this condition. Okay, so actually we follow certain steps here, and finally we'll end with at one point, so where the remainder equal to 0 and the procedure stops with, that is HCF. Okay, and so here drawback also sometimes he asks. So it is not useful for the decimal numbers. You cannot apply for decimal numbers. Example, find the HCF of 0.12 and 1.2. This question is there. Of course, we can find out HCF. That is a different manner, but we can't apply this Euclid division lemma for these decimal numbers. What we do in case of if you want to find out HCF here, so 1.2 you can write as 12 by 10 and 0.12 you can write as 12 by 100. So how to find out HCF? Very simple. HCF of numerators by so LCM of denominators. So here 12 comma 12 by LCM of 10 comma 100. So that way you can find out. But that is not I am talking about here. So but 0.1 to 1.2 we can't apply Euclid division lemma algorithm to find out HCF. So we will find out this manner, not using this division algorithm. Okay, clear? So 3 points I told you. So this is useful for to find out HCF of huge numbers and to study the number pattern, to prove the number pattern. And the second one, this is also applicable for negative integers. And the third point, so here it is not applicable for the decimal numbers at all. Okay, but we will find out in a different manner for the decimal numbers. Okay, without using Euclid division lemma we can find out HCF of decimal numbers. Now let's see the next one, terminating, so non-terminating. So terminating, non-terminating, x equal to any rational number which is in the form of p by q. Okay, so if q is written as the prime factorization of q written in the form of 2 power m into 5 power n. So these two you can interchange, 2 power n into 5 power m also you can write. So then the rational number is terminating. Example, 7 by 2 is there, so it is terminating. Okay, how do I know? Because the denominator equal to in the form of 2 power 1, 2 power 1 into 5 power 0, because 7 by 2 into 1 we can write. So 7 by 2 power 1 into 5 power 0 is nothing but 1 only. Any number power 0 equal to 1 only, no? So likewise, so which is in the form of 2 power n m into 5 power n, terminating. Not only this, so if the denominator is 5 also, only 5 also terminating. If the denominator is both combination also terminating. 7 by 2 power 3 which is equal to 8, only 2 is, and the powers of 2 like 2 power 1, 2 power 2, 2 power 3, 2, 4, 8 and 10, okay, 16, 32, so likewise. So the multiples of, if the denominator can be written as multiple of 2, 2 power something or 5 power something, and 2 into 5, 2 power m into 5 power n, then always terminating. Other than 2 and 5, if you have the other number, so then you try to eliminate it, try to cancel it after doing prime factorization method. Otherwise, so it is not terminating. Example, let us see in a different manner. Okay, easy way how to remember this one. So example, 2 equal to wife. So don't think otherwise, children. Husband, I have written husband in a shortcut manner, so husband. So here wife equal to 2, husband equal to 5. Let us imagine. So if I have a house here, house can be run by wife. Only wife is there, that is also okay. Okay, so wife leads the house, and even husband alone also can lead the house. Okay, this is also possible. Now both are there, that is also well and good. Wife and husband also well and good, both will read. Now the problem begins here. So when the wife and husband is there, or wife alone, wife and husband with some other person 3, problem begins. No, non-terminating at all. So only one number, any number with only denominator 2 or multiples of 2, not multiples of 2, powers of 2, children, not multiples. And here only any number with a denominator 5 and powers of 5, so always terminating, and both 2 and 5, so that is also terminating. But other than 2 and 5, if you have any other number, that is non-terminating. Okay, right. So this is only concept. So while we are solving exercises, all the sums you will understand more clearly. Right. Now let us see what is the fundamental theorem of arithmetic. It's a very simple. Okay. So any composite number can be expressed as product of prime factorization. So the prime factorization is unique in which the prime factors occurs irrespective of their order. Very big statement is there. I'll make it very simple. See, if you take any composite number 8 can be written as product of prime factorization. Say 15 is there, 3 into 5. So 3 into 5 you can write as 5 into 3 you can write. However, you have to use 3 and 5 only. Whoever in the class, whoever in the world may factorize, they have to use 3 and 5 only. Some people will write 3 into 5, or some other will write 5 into 3. However, both are equal, no? Both 5 will come, 3 also will come. So this is called unique factorization. Means however upside down, however you do, you will get only 3 and 5 only. So every composite number can be written as product of prime factors, which is nothing but product of prime factor. Expressing a given composite number as a product of prime factors is nothing but fundamental theorem of arithmetic. That's it. Okay, that's it. Okay, so now let us see irrational number proofs, which is a very important, definitely 4 mark question, most of the cases. So you have to know what do you mean by actually rational number plus irrational number plus or minus is always irrational number only. Example, 2 plus root 3 equal to irrational only, and 2 minus root 3, so it is also irrational only. Okay, addition or subtraction always irrational number. So but whereas q into q dash, okay, q into q dash also irrational only. Okay, so and q divided by q dash is also irrational only. But whereas if you take the combination of two irrational numbers, so that can be rational or irrational. That is the only problematic here. So if you take two irrational numbers, that is root 2 into root 2 product, that is equal to 2, again rational number. So root 2 into 3 equal to 3 root 2. So again irrational, rational, irrational. So only problem begins when you take two irrational numbers. But whereas when you take plus or minus, okay, rational, irrational, the sum of rational and irrational always irrational, and the difference also irrational, product also irrational, division also irrational. Okay, when you take rational number and irrational number, but when you take two or irrational numbers, so the answer can be rational or irrational. Okay, remember that. Okay, now in this category, so you have basically two types of questions. Single irrational number is a combination of irrational numbers. So prove that the given numbers are irrational. In that case, you need to apply squaring on both sides, and here it takes time. So it's a lengthy answers here, and here you need to take, let finally at one stage, let k is equal to 2c or 3c, whatever the number you are taking, so the same you have to take. And here directly here also you need to apply squaring on both sides, because given two numbers are combination of irrational numbers. But the second type, one is rational, the other one is irrational. So and rational, irrational.